Good day to you. This is ANAGALACTIC bringing you a presentation in geometry where today we're going to drill down even further into the heart of the atom using the work of an amazing man of the 18th century named Roger Boscovich. And Roger talks about Newton and Leibniz quite a lot in his Theoria Philosophiae Naturalis, where his force curve appears. This is the document that I prepared today to give us just a visual guide to what's going to transpire here. We'll be studying space-time. Invented essentially by Albert Einstein, and even the inventor of the geometry, Minkowski, gives credit to Einstein, and it was Minkowski who first came up with I'll just say the pattern. He understood the structure that he was looking at, and understood that a 4D space-time relation was required. And he understood that 4D would be useful for that. And so to this day it is called Minkowski space. We're not going to delve into that aspect of space-time, but it is important to know what it is we're trying to understand and why. So let me just repeat that the reason we need to know about space-time is because only in that formulation can we achieve our final goal of understanding the propagation of light in the universe, which has enormous, I'll just say at least potential, to unlock the secrets of the universe for men on an individual basis. It's always tricky to predict, but in general that's what we're working toward, is a new vision, a new form of vision, a new perception of reality that improves us. It has to begin at an individual. That's true in any situation where there's, for instance, we're looking for some goal for humanity, perhaps. Oh, certainly, we're all in this together. But we will not, any of us, achieve anything together. It's not every man for himself, but in the sense of understanding, it absolutely is every man for himself. Nobody can do it for you. So in our approach to space-time, we wanted to disambiguate what it is, first of all, that makes it so complicated, so frustrating, so agonizing, and really terrifying. I tried to understand space-time about once or twice a decade for about 3 decades. And it just took me that long to come back to it. Similar to my experience with the book of Revelation and the Bible, where the other books, I would tackle them one by one, but Revelation I kept coming back to because I couldn't understand it. One can be persistent, but then one must at least have some form of faith that there actually is an answer. Well, we subscribe to the Einsteinian principle here. Of course there's an answer. We're blueprinted to find that answer. And we are guaranteed, not just by religions or any single religion. In fact, we're not really concerned with religion at all, except perhaps as individuals. I certainly am, but I don't share it. But in science, it's absolutely a form of logic to have some kind of expectation. Otherwise, it's illogical what you're doing. And it may sound like Vulcan talk, you know, that is illogical, Captain. Absolutely right, Spock. And we humans could sure learn a lot from Mr. Spock aboard the Enterprise. So what we're doing is capitalizing on our absolute faith in the total reliability of the universe to supply us with the answers that we want. And Einstein definitely crossed a bridge. He got time into space. Now, the significance of that for us as astronomers in the long run, I'm speaking for myself, but I'm certain that I am not alone, and anybody can share this to their benefit. We need to know about light propagation. One of the keys to the universe, certainly in consensual science, but this is a human concern, and I don't think this is I don't think this is shunted off to the mathematicians and brainiacs who, with their wide eyes staring at their blackboards, understand so much more than we could ever understand. I'll show you in this sequence that is never true. You must never rely on the blackboard people. You may need their training, particularly if you want a job. But the purpose of school learning is to enable your actual progress in science, which really has nothing to do with any university. So, that's our philosophical approach. We want to understand space-time because we expect to be enlightened. I can definitely tell you that expectation is justified. You will be enlightened, and I'm going to do my best to assist that you become enlightened. Exactly as much as you want, or even dare to hope, and oodles more, this has to actually go to infinity. We need to be on the right track. That's the whole idea. Now, you may think that's deep philosophy, but what I'm going to show you today, we begin by proceeding. I just wanted you to see that. This is the Boscovich force curve with an expansion of part of the curve. And if you've never seen this before, it could look a little daunting. I guarantee you that sentiment is shared even by people who work with diagrams like this. Back in the 18th century, it was common to use just one diagram for several illustrations. And so there's more than one end being achieved by all of these letters peppering the diagram. Even Ruger made a note in his book, which I read, that he's aware that it's a little crowded in that diagram. And I believe it was for the purpose of parsimony, that you just want to save space and let the student, get along as best he can. I don't really subscribe to that method, but it's perfectly normal to do so. So I don't really have a pointer. I can see the pointer on my screen, which you cannot. So I did my best to arrange this so you would be able to see just what the Boscovich force curve is. And if you've never heard of it, it's one of the most amazing things that I have ever seen. I'm not a mathematician nor a physicist, nor do I care too much for this kind of diagram because I associate it with sine waves and basically calculus. So, which I've also tried to tackle several times in my life and was finally able to break through. Again, about once or twice every decade I tried again to understand calculus, but I have a kind of a mind that if I'm balked at the beginning, I won't go on. I'll stay and try to figure out the initial problem because I don't want to build on a false foundation. Now in school you have to get over that commonsensical point of view. You have to force feed yourself and you have to be stuffed like a Christmas goose with data. This is well known. I'm not talking out of school here. So let's do it the right way. The Boscovich force curve intends to describe the relationship between two particles. If you know even the rudiments of scientific history, in the 18th century there weren't any particles. The closest anyone ever got to discovering even an idea of a particle, it came about with the Greeks, that Democritus is accredited with the idea of the solid ball building block. Consider it to be like a grain of sand on a beach, and the beach would be the universe, but it's made of grains of sand. Now what Roger noticed, because that's how Newton looked at things, and when Newton interpreted light, Newton didn't like spooky action at a distance, and you can look that up on the internet to find out what Newton thought about spooky action at a distance. Well, you're going to have to get used to that because that's been proved to exist, and that's actually what you and I are going to discover directly for the first time in scientific history right now. So I want you to know what we're in for here. You're going to understand space-time from this diagram. And in the next lecture or two, I'll show you how this also describes the quantum paradox, so that it's no longer a paradox. All of that comes about from this force curve, which Ruger devoted the second half of his life and exclusively, even with his immense responsibilities as a Jesuit priest professor. There, talk about overwork. You'd have to take a look at Ruger's life to understand what overwork is like. And yet he was able to do an incredible number of things in his lifetime, including having a hand in the discovery of Neptune. So he was no slouch, not at all. He was a real physicist, and he inherited the robe of both Newton and Leibniz, which Boscovich promptly, on the first page of his magnum opus, which we're going to look at now, he said that he had something to add to Newton, and he needed to correct a few slight mistakes of Leibniz. And then his work was basically not entirely forgotten. Faraday knew of Boscovich's work. So did Tesla. And it is known that Einstein knew of Boscovich's work, but never really commented on it. But the amazing thing about Roger's work, when you combine it, one fact with another, is that he was totally ignored. He doesn't appear really in any textbooks. He was the most famous mathematician, really physicist, in Europe after Leibniz and Newton. There was no one that even was close to Boscovich in expertise in mathematics and geometry and physics. But he was also a visionary, and I mean that in the highest sense, that he saw way ahead of his time. So let's get into the Boscovich force curve, otherwise I'll end up just praising Boscovich to the skies. But I am intending on being the leader, or one of the leaders, in a movement which is worldwide now, mostly in Italy, but also throughout the continent. Not so much in America, but there are a few men, and I'll be naming some of them, such as Augustus Prince. Augustus Prince has some amazing insights into Boscovich's force balance system. This is actually a reformulation of mechanics. And I will tell you, point blank, under the eyes of God, he's absolutely correct. And it does improve on Newton. Newton only knew of a one-force system. He had no idea what to do about centrifugal force. It was not something that entered into his calculations really anywhere, except to the extent you may have heard of his experiment with, well, really, it's not a Gedanken experiment because you can do it. But you can spin a bucket of water, and it's very interesting how to explain why the water stays in the bucket. And another thing, and that has to do with centrifugal force, which is out from a center. Okay, these are the two forces that balance the entire universe. Emmy Noether actually gave us the key to making that statement so that it's absolutely true. So we now know really more than the physicists know, because the physicists got sidetracked in the 19th century with another kind of mechanics, which was much better suited to industry. This is not suited to industry, or I should say, it could not be considered as suited to industry as basically, there's several names for the kind of mechanics that are used. Hamiltonian mechanics, Jacobian mechanics. There are a couple of others, excruciatingly difficult even to look at and imagine understanding, because all of these systems are based entirely in complex numbers, and the calculus is always there, just filled with irrationality, just all kinds of tricks and traps, and it just doesn't really work. And that extends all the way to quantum mechanics and to space-time relativity, Einstein's formula for gravity. Boscovich has a much better system. It's mathematically sound. I was able to prove that in 2022. Although I didn't know about Boscovich's work. I found out that I had proved his work without knowing that's what I had done. So this is an amazing synthesis of ideas where this little professor just happens to have stumbled into a gold mine. So let's get into it here. You'll see in the top diagram, it's just basically a repeat, but a much simpler repeat. But it's marked with the abscissa, which is labeled space, and X for the X, that's the horizontal axis, of course. The vertical axis, in Roger's day, that was called the ordinate, and you may have heard that in grade school, but not very many people use it these days. But it's a good word to know. The ordinate is force. Now that's a really interesting, that's of course perpendicular, so this is an orthogonal relationship as depicted on the graph. It doesn't mean it's orthogonal in physical space, but I'll show you it actually is, but not in linearized physical space, which could hardly be said to be physical space. It's a grid that's overlaid really onto space. So that's the nature of our linear system. I've discovered the spherical number system and spherical geometry, which is much more appropriate for subatomic particle physics and for deep space astrophysics, such as for the supermassive black hole, which we're going to get to that because I've made an incredible discovery in that area too, entirely due to this geometry. So let's proceed apace here. The second diagram down in color has a little more information. The horizontal line is the path of one particle towards that bullseye that you see on the left. So the path of the particle, which we are going to say is an electron. And I don't wish to confuse you, and I hope that I don't confuse you, although this did confuse me when I first saw it. So I'm just going to give you a heads up. Because Roger did not know of any particles, he was basically in the same shoes as Democritus and Newton in just presuming that there must be such a thing as a particle, but not even, well, nobody knew what an atom was, and nobody would know what an atom was for over a century. So this is remarkable that he actually got it right, just on the basis of his incredible insight. It was geometry, and he admits it's not mathematics. The mathematics has to be there, and don't worry, I've proved that if you get the geometry right, the mathematics will also be correct. It's worked the other way these days, because mathematics is now considered to be so powerful, and really rightly so, that it's worked the other way, that you'll end up getting the right geometry by manipulating the mathematics. That very rarely works, and it's not working. Neither in quantum mechanics nor in astrophysics is the method of juggling the mathematics to try to get a better geometry. They'll never do it. In fact, that's not the only thing that's halting the progress of science. Not to worry again, I have all the solutions. It's not to be presumptuous, it's simply a fact. And it doesn't do any good for me to insist on that, and in fact I don't insist on it on your behalf. You must get the proof. You can never rely on a human. Really, technically, a scientist doesn't even rely on himself. He won't believe what he's pretty sure he's seen until he can prove it to himself. So that's what we're doing here. The red line labeled electrostatic force is a tremendous boon for you and me to understand this. It doesn't have anything to do directly with the orange curve, which is what we're studying. It's put in order to show what this graph means. Now here, I want to complete my former sentence. Since Ruger did not know anything about an electron or a proton, we have to fill in the names of the particles. And there are 3 possible interactions. Proton to proton, electron to electron, and the most common one, of course, well, the one that makes the atom, is proton-electron. That's the definition of an atom, is a proton-electron system. But he didn't explicitly know about those particles because nobody did. Even though the force is spherical in any one direction, it is a straight line. There are only two basic curves, and we see them both here. So the top curve, which just shows repulsion, that describes proton to proton and electron to electron. When protons are very close, such that they've passed a certain, it's really a binding energy perimeter, is access to this immense energy source, which is inside the proton. It is, though, I know it is, and they're absolutely right. They'll never get it. They'll never figure it out. It's possible that they could figure it out if they use the correct geometry.
So I could be assisting inadvertently and ending the world sooner than it might. It doesn't bother me a bit.
This, by the way, is Martinelli's cider. The electron is coming in. When it reaches the 3 femtometer hash, it starts to accelerate very rapidly until it reaches the nadir, the bottom of the curve. Now, at the bottom, it's achieved maximum velocity. So it's going as fast as it ever will, because at the nadir, that's a tipping point. As it's at maximum velocity, when it crosses that imaginary point, or imaginary dividing line, the infinitesimal of symmetry, from that moment forward, it's decelerating. It still has its velocity, but it's decelerating. So what does this graph actually tell us about what happens as the electron accelerates toward the proton? If that orange line had continued to dip, it would mean that the electron collides with the proton. But that doesn't ordinarily happen. And the reason is, there's an even stronger force that the proton emits. It's difficult to talk about how a field is generated from a particle, but that's exactly what this graph shows, is that the proton emits a force field. It's a complex force field. Gravity is a single force field. It's pure centripetal force as far as we know. Gravity is not consistent over cosmic distances. That hasn't been proved yet. I'm stating it because it will be proved someday. The reason dark matter was invented was to explain the fact that galaxies don't just have gravity. But you see, it's assumed that that's all they have is gravity. That simply is not true. That's not true. Gravity is not the only force at work in the universe at macro scale. And that's going to be a very, very far-reaching insight for you, me, and for physics. What we want to do now is understand from this diagram why that would affect gravity. It's because gravity is an integral force based on protonic concentration. You may know that mass is measured in, protons measure mass. Well, I could say it either way. Protons and mass are exactly the same thing. There's a footnote, except that what I said though. Protons are mass. And the reason that they're mass is that they have centripetal force, which means that they pull towards their own center. The way Albert Einstein explained this, and this is accepted, and you can accept it for now, but I am going to show you a better way to visualize what gravity is actually doing when it's interpreted as integral protonic centripetal force. It's bending space. It's contracting space is technically correct, but Einstein said that space bends. That is what Einstein said. Space bends. That is probably the greatest discovery in the history of science in its class, because space has always been conceived as having no properties. But it does have one property, and that has been proved. Space bends. The reason why this is still controversial and still somewhat baffling is there's more than one framework in which to interpret gravity in conjunction with subatomic force balance. And it's not that any one way of saying it or looking at it is right or wrong. It's that depending on context, you may prefer one framework to another. And so I want to give you a clue that's going to be of immense value to you. And that's the difference between space curvature, that space-time is curved. Space-time is curved. And the reason all of our physicists believe that space-time is curved is because that's what Albert Einstein's formula says. It's not that space is curved by itself, is that space-time is one thing that is curved. That is incorrect. But it's so close to being right that we can use calculus to just sand down the edges. Well, if you're trying to understand the universe, you can never do that. You can never sand down the edges because you're sanding away part of reality. When we build our machines to specification on Earth, including microchips and rockets, we are definitely cheating the universe. We are able to succeed because we know the structure well enough. But here we're at the limit. And this really embarrasses us. Physics has its pants down around its ankles right now. And it doesn't know why. So it's really not a matter of shame. It's just a matter of grief. That nobody knows how to get out of the space-time curvature bind because it's considered to be the very words of God. Nothing less than that, except these men actually don't believe in God. None of them do. There's always exceptions, but statistically, they fall into a certain type of man, which I don't believe belongs in science. It's all right to be a hypocrite in a church. That's what churches are for, to gather the hypocrites together. But in science, we actually don't want you if you're too stupid to admit your errors. So it's okay to make errors, but it's not okay to teach errors. All right. So what we're looking at here is a dual force system. Well, that absolutely buries Newton. Now, Boscovich was not in competition with anybody. Both Newton and Leibniz were dead, and apparently Newton and Leibniz at least generated controversy between their two people. Again, I don't like that, but that's part of history. But Boscovich was not even... I don't think he had any rivalries. Of course, as a top-notch physicist, you would expect that, he was involved in controversy. He was with the Pope over some things, but really nothing in physics. He was the unchallenged expert in Europe, and none of his work has ever been even challenged. That's to finish a sentence from quite a while back. So, all right, that's 45 minutes, and I haven't gotten very far into this. But I don't think that this is wasted time. You can see that we're getting into something so deep that most people would be absolutely paralyzed, or they would turn their tail like bunny rabbits and run away. I hope that you trust me enough to realize that I am just about to teach you. I'm just going to leave it at that. I hope you tune in for the next presentation. And I want to make a comment here before signing out. The ANAGALACTIC.SPACE site is up and running now, and I urge you to take a look at that. It's rudimentary, but you will be able to download a PDF just so you can see that it does something. And it does show the information from U1, the Unimetrics presentation number 1, which was yesterday. This is presentation number 2, and our goal is to fully understand space-time. And more than that, I'm promising you, when I'm done, I believe it'll take, I don't want to make predictions, but I'm guessing this will take about 6 to 12 presentations of about a half an hour each. This has gone 45 minutes, but I'm getting better faster. Within a certain amount of time, I'll just say before summer, give myself some room. This is remarkably easy. There's nothing complex. Well, there's nothing complicated about this. In fact, I consider this to be one of the greatest joys of my life, because I've always been afraid of mathematics and afraid of physics, afraid of this stuff. But I'm so vitally interested in it that it's really torn me in half all my life, that I can't understand space-time and quantum mechanics. I wasn't that interested in quantum mechanics, but space-time, yes. And I think it's safe to say we all want to understand it. Well, you're going to, but I want to just both warn and encourage you. You will understand space-time better than all the physicists. You will. And don't think that that's so far-fetched. It would be to put yourself down and indirectly to put me down too. It's difficult to assess when to take a chance because we don't have much time in this life. And we don't like deceivers because they waste our time. Well, I'm not going to waste your time. I am involved in this emotionally. I want this to be known. I will publish. I have to. And I'm still going through a roller coaster ride on this because I know what's going to happen, but I don't want that to happen with my listening audience. Science will not accept this. And I'm just going to be frank with you. It won't accept you either if you understand this. This is only going to be for you and me. And so the payoff that I promise you is you're going to have a new vision of the universe that's going to change not just your life, it's going to change your being. It's going to change you vitally and dramatically and ultimately for the best. I'm talking about pie in the sky by and by, Shangri-La, Valhalla, heaven, bliss, permanent peace and joy and excitement. That's what it's done for me. So I hope it does that for you too. And we'll be right back. This is ANAGALACTIC. Don't forget to keep looking up. All right? Because I'm not just saying that to have a byline, something I say at the end of every lecture. If you go out at night and just look, it's not always easy, I understand, but when you get a chance, don't turn it down. And try to extend it as long as you can. Keep looking at those stars. I don't care if you're just looking at the moon. When you do that, you have no idea, really. It's not possible for a human being to fully comprehend what that does for your mind, body, soul, spirit, and system. Because your body has a feedback system. It's garbage in, garbage out. But when you're looking at the night sky, at the stars, planets, moon, especially with a telescope, that never hurts. Binoculars are even better. Well, it depends on what you like. But look at it for a long time and try to get the clearest night sky you can, because it's the best time you'll spend on Earth. Minute by minute, the payoff is forever. And the rest of your time you spend on this miserable goddamn planet just getting closer and closer to the grave, you'll regret that part compared with the time you spent looking into deep space. As far as you can see, it's an instinct, it's blueprinted. And of course that means it's blueprinted by superconsciousness that wants you to do that. It or she. It or she. I've been corrected so many times on he now by modern he then. All right, that's enough. I hope you're having a good time. I certainly am. I will always have a good time. No matter what kind of emotion comes out of me, I am in heaven already. Even as the Son of Man is in heaven. Stay tuned. This is ANAGALACTIC. We'll be right back.